All right, everybody, we're going to continue our exploration of mechanisms in Chapter 18. Chapter 18, we always have to remember, it's all about functional groups that are derivatives of carboxylic acids, with acid halides being the most reactive. And a close second is acid anhydrides, not on this page. A distant third, esters, and constantly reminding you, even though I wrote this here, I expect you to be able to tell me it's an acid halide. Even though I didn't write it here, I expect you to be able to tell me this is a secondary amide with a D. This is an ester. You need to be able to tell me that. You need to be able to draw one on the nomenclature on your next test. And this is a primary amide with a D. And the leaving group is an alcohol. So starting off here, we're going to take extensive use of red first and blue second. Because almost every mechanism we see today is going to involve attack by a nucleophile, pi breaks, lone pair created in that step, resonates back, kicks off the leaving group. Get used to it. It's the poster child for reactions of carboxylic acid derivatives. And here we go. We have this species here. We have a nucleophile on here. And it looks like this is one of our easier mechanisms because it's almost done. What is our best base for taking this proton off? And yes, you remember way back from Chem 241, Organic Chemistry 1. The most important thing about amines is that they are bases. We have excess amine available here. H2N, CH3, lone pair. We're going to see a similar situation with our next one. In fact, I hardly see any difference at all. Here we go. Normally, a catalyst is needed. You'll go back on last day's videos and you'll see I said esters and amides will typically need an acid catalyst. Why do they not need an acid catalyst in this reaction? It's because your nucleophile is more reactive. It's nitrogen. It's pushy. None of these words are new. The nucleophile attacks the carbonyl. The pi breaks. The lone pair created resonates back and kicks off the leaving group. Sorry about the crossing arrows here. But having two colors, it's clear the red and blue are different things. So we have our carbonyl, and it looks like this is a smaller molecule. I didn't notice that. Carbonyl, NH3 plus. And you're saying, oh, he said it's exactly the same mechanism. But you know, being savvy organic chemists and our knowledge of pKa's, we see that, yes, NH3 is a good base, but it is nowhere near as good a base as the conjugate base of an alcohol, which is what I just drew there. So that better be your base. And there you go. Why did Cl minus not do the same thing here? I think you know the answer. Cl minus is nowhere near as good as base as an amine. Why did O minus be the base? Why was O minus the base here? It's a better base than an amine or ammonia. And that's the end of our quick little activity today. We'll come back with more mechanisms, all day mechanisms.